All right, let's get right into it. If you're sitting for the Cambridge Physics 9702 exam, there is this one specific trap in the solid-state physics section that literally catches out thousands of students every single year. It's a micro topic that seems, incredibly simple on the surface, but if you don't structure your answer exactly the way the examiners demand, your grade boundaries are put at serious risk. So today, we're breaking down alloys and ordered mixing in this explainer, and I'm going to show you exactly how to secure every single mark.
An alloy is a mix of metals that makes it stronger. Now, if you asked 100 students to define an alloy, honestly, 99 of them would write something exactly like this. It's that typical everyday language shortcut. It sounds logical, it feels right, and well, it completely backfires on the exam paper. And here is the brutal truth as to why. That scattered, unstructured answer scores exactly 0 marks on the rigorous Cambridge mark scheme. 0. No way around it. Why? Because the examiners are not testing your everyday vocabulary, right? They're testing your physics. Stating a generic result without explaining the physical underlying cause is just a guaranteed way to lose marks. We absolutely have to leave that everyday language behind.
Let's move into Section 1, inside the crystal structure. To stop bleeding marks, you have to stop looking at the material from the outside and really start looking at what's happening on the inside. Ordered mixing is the predictable internal arrangement of atoms in a solid. And this predictability controls 3 critical effects. First, packing, which is how tightly atoms squeeze together. Second, bonding direction, which refers to the specific geometric angles of those connections. And third, defect tolerance, which is how well the material actually resists cracking under stress. You aren't just mixing metals here, you're fundamentally altering the crystal's entire architecture.
Now, to really master a topic, you have to know its boundaries. So a crucial point is understanding the difference between ordered mixing and a nearby concept like random solid solutions. In a random solid solution, the atoms are just scattered haphazardly. There's no real pattern. But in ordered mixing, just like the name implies, there is a very specific, predictable geometry. Knowing this distinction for sure ensures you don't confuse related ideas during the high pressure of an actual exam. Which brings us to the fundamental physics question you absolutely must ask yourself every single time you face this topic. What happens internally at the atomic or carrier level? If you start from the macroscopic phenomenon and work your way outward, rather than just, memorizing labels, you end up building this incredibly robust understanding that examiners just love to see. In just a second, I'm going to show you the examiner clue that changes your answer completely. But first, you need the framework that makes that clue obvious. Because honestly, without the right framework, even the absolute best clues are just going to slip right past you.
Section 2, the high mark answer framework.
Okay, this is your mandatory 4-step path to full marks. Step 1, define the concept. Step 2, describe the microscopic mechanism. Step 3, identify the measurable consequence. And finally, Step 4, connect it to a real-world application. Master this specific sequence, and I promise you can effortlessly handle both the short and extended exam questions. A disciplined paragraph that clearly connects cause and effect is always going to outscore a scattered collection of random facts. Section 3, real-world physics applications. Examiners want to see that you understand why this stuff actually matters in reality. So here is your menu of high-value examples. We've got semiconductor wafers, where ordered mixing totally controls carrier-level behavior. Turbine blades in aerospace, where extreme defect tolerance allows them to operate at temperatures hotter than their own melting point, which is just wild to think about. Then there are structural alloys used for incredible strength, and gemstones, where the internal arrangement dictates their actual visual properties. Pick one, know it inside and out, and be ready to deploy it. Section 4, the top band answer reveal. All right, it's time to finally fix that deeply flawed answer from the start of our explainer. Remember the mix of metals that makes it stronger response? It's lazy. It's an application without a microscopic reason. Now compare that to the top band answer, which completely abandons that casual approach. Instead, it systematically uses our 4-step framework to explicitly map atomic cause straight to measurable effect. Let's map it out perfectly so you can see exactly how it works. Concept: we establish there is an ordered mix in the solid-state crystal structure. Mechanism: this predictable arrangement controls the atomic packing and bonding direction. Consequence: this fundamentally alters and increases the material's defect tolerance. Application: and it's this extreme defect tolerance that prevents turbine blade failure under high stress in aerospace engineering. Do you see how perfectly that flows?
Cause, mechanism, effect, reality? That right there is a top band answer.
Section 5, the final memory trigger checkpoint. Okay, I want you to literally answer these 4 prompts out loud from memory right now. Ready? 1. What is it? 2. What changes inside the solid? 3. What can we observe outside? And 4. Where does this matter in technology? Seriously, if you can answer these out loud right now, your understanding is completely secure. You have successfully locked in the definition, the mechanism, the consequence, and the application. So, you've absolutely nailed the ordered mixing trap, and you have your 4-step framework ready to go. But what about the rest of the paper? While you'd secured these marks, there are other hidden traps waiting in Physics 9702, specifically in data analysis and practical investigation questions, and they are designed to quietly steal your grade boundaries if you aren't prepared for them.
To make sure you have absolutely every tool you need to master the Cambridge syllabus, subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We're essentially building the ultimate defensive playbook for your physics grades.
In our next explainer, we're breaking down the common traps hiding in those tricky data analysis questions and the safe shortcuts you should be using instead. But before you go, ask yourself this. If a topic as seemingly simple as alloys was hiding a 0-mark trap, what other tiny microscopic details are currently risking your grade boundaries? Head over to our next explainer to find out and protect your grade. I'll see you there.